an example related to the calculation of inertia values for a given example in the wiki. Now it's time to implement those practice into a robot, right? So all of our parts for the robot were made from cylinder, right? And that was intentionally done to make things easy for us. Now we have to apply this inertial matrix to our robot, each and every single part of it. If we open up our bigbazoo.urdf, and let's start from the first base link. And base link is a cylinder of this and this radius and length. We need to write the equation here as well. 1 by 12 into m, and that is going to be multiplied by 3r square plus h square. 3r square plus h square, 3r square plus h square for ixx, iyy, and then mr square. 1 by 12 into. I'm just going to bring this to the URDF. This is the equation that we need to implement in the inertial part. Let me remove the origin, or let me keep it with our robot. So mass value is 5 for the base link. Let's start applying it. Ixx, which is, we need to open up the calculator as well. 1 by 12, we will multiply by that. Radius square plus height square. Radius square 0.2 square plus length is 0.05 square. Let me give brackets around it so I can apply this equation again and again. 3r square plus h square. Is that correct? Yes, it is. 3r square plus h square, and it is going to be multiplied by 1 divided by 12, and it is going to be multiplied by that. So I am going to copy it because it is going to be required again and again. 0.01. Where is m, by the way? I missed the m part. So m was multiplied from in the outside brackets. In our case, 5. So 0.05, 0.051, 0.051. That was our ixx. This is ixx. This is iyy. 3r square equation is the same. So it is going to be the same. 0.051. For iyy, that is 1 by 12 mr square. So 1 by 12 and mr square. What was r? 0.2 r square. We need to just multiply m here and 0.05. That was already there. So base link seems to be done. We need to move forward. And link number 1. Link number 1 values were very fine. Let's check them. We need to just add the mass 5. Length is, height is 0.05 and radius is 0.08. Let's take a look. 0.112. 0.112 and iyy is also 112. For the second part, or izz part, I need to copy this. Mass is given 5. Mass value is actually the value that we give by ourselves. Okay, so 5 and 3 mr square. What is r here? R is 0.08. What is length? 0.5. But it is just the r square for zx, izz. 0.008. So that's it for the base link. The problem we were having were from joint 1 to joint number 5. So I am going to fast forward the video from this point, and we will complete all of the values with the same procedure that I showed you. All of these equations are going to apply to our robot. Okay. To some extent, all of the values have been applied to our robot, the inertial values, and it's time to take a look how does our robot looks like in physical properties in Gazebo. So we need to open up the terminal, navigate into the workspace we were working on, and perform calc and build, as we have made a lot of changes in the UIDF. That's done. Now we are going to launch our robot in Gazebo using the launch file. We did not did that earlier. ROS2 launch, name of the package. I'm pressing tab, it automatically completing. The name of the launch file I want to run, gazebo.launch.py. It opens up a lot of things. Let's see, does it work? No, because I've already running Gazebo at the backend, so I will perform kill all GZ server. It killed all of those behind running servers of Gazebo. Let's run it again and see how does it looks like. So it tells me about the joints, links, and their connections. So this is our robot, and moment of truth, we need to take a look to the inertia values. And to some extent, the big box is now gone. You can see it. For the base and this link number 1, we can see for this small cylindrical base, we have a big box because of the big mass, as 5 value was given to it. Now this bar is having an inertia box inside of it. That's work fine. These two joint circular discs are having inertia values now inside them. The problem here still resides with this thing. What is this? And at what angle it is representing the inertia values? So we have a problem that we need to solve in the upcoming lectures, and I leave it to you. You solve it. What is the problem here? How we can solve it? There is a very small fix to solve this issue and make it move on the body where the inertia has been applied. So to some extent, the inertia value has been solved, but still there is a problem. From now on, we are not going to be working on these things because they are solved to some extent where they can work very fine. We are going to be moving towards installing controllers into this robotic arm and not make it move freely the way it is moving. Okay, so let's move towards the next thing, and that is ROS2 control. To make our robot stand still and make it move accordingly with our requirements, in Gazebo we need to have control. Now ROS2 control comes into play when we are dealing with controllers in our robot. We need to first understand and look into what the basic architect of ROS2 control is. So this diagram might confuse you a lot, but let me give you a brief introduction and we will do it practically to make more sense out of it. First, we have the controllers. There can be multiple types of controllers. We'll talk about that later. But first we need to have controllers that are going to be talking with the control manager. Control manager is the major thing. You have to build the idea about it, that it controls the update functionality for all of the communication happening with the script and a real robot or gazebo simulated robot. So controller manager is in the middle, talking from a software script, which is a controller, with the robot. Okay. Resource manager comes after controller manager. Controller manager was the main. Resource manager loads up all of the components using plugins, libraries, and manages their lifecycle. The basic definition of resource manager. It is not going to come up explicitly as controller manager, but on the back end, it is going to be doing a lot of stuff. Resource manager now deals with two important things: command interfaces and state interfaces. ROS2 control provides us a very interesting thing, and that is command interfaces and state explicitly. They are two different things. Command interfaces are dependent on the controller type we are utilizing. State interfaces are read-only. We can get information in whatever type we want. For example, commands we are sending are position commands. Make your robot or joint move to 30 specific position in radians, 30 degree let's say. And in return, when we are reading, we can read its velocities, we can read its position, we can have multiple interfaces. This is a very important point to focus on. We are sending rotate your robot's wheel at a velocity of 30 degrees per second, let's say. When we are reading it, we don't need to convert that into current position. We just read the position of our wheel. So state interfaces gives us a lot of power when we are reading with multiple interfaces. Command interfaces, when we are just driving the robot, we are not making ourselves difficult in programming. When we are rotating the robot, we just send rotating command. While reading, we just read this static command. So this gives us a lot of power. Coming to the next portion, which is sensor system and actuator. We can define our robot in a system, which contains a lot of things like multiple actuators, complex kinematics, and sensors and actuators included in that. But we can explicitly define actuators and sensors explicitly other than the system. That's the user freeness, what I call, is provided in ROS2 control. And you might be thinking that controllers are going to be big code, but they are not. They're simply one single script in general that can perform any type of controller you want to install into your robot. Isn't that cool? Controller workflow is what I'm going to talk about right now. We have a lot of options, predefined options like position, acceleration, velocity, and much more effort, and then group of those and then joint trajectory controllers. We will be looking onto the basic one just. We can write our own custom controller as well, and things can be made the way we want them to work. The position controller. As the name suggests, we need to distinguish between them. Position controller is going to be dealing with just the positions. We will tell 30 degree of joint 1. It will make the joint 1 to move to 30 degree. Acceleration and velocity same, but they are not going to be very useful for robotic arms in my perspective. Acceleration and velocity will be more useful for differential drive robot, okay, where we need continuous motion for your robot. For robotic arm, we just need positions of our robot, the joints of our robot, and we want it to move. For example, this is the base, and then we have a link, then another link, then another link, and we want this to come to this point P1, this end effector point. We want it to come to point number P2. So this motion, all of these joints which are included in the robot are going to be included into the motion and make the robot go point from P1 to P2 at its end effector. This is going to be done with a very easy controller, and which we will be looking into is joint trajectory controller. We will just tell the position, and whole of the robot joints will adjust themselves to move to the point number P2, and everything of this such motion is going to be done by joint trajectory controller. It will take care of all of the things and produce a smooth motion. Position, velocity can be used to make the robot move, but we will not be using it. So how actually to install a controller is an interesting question, right? I have described it in 3 terms. The first part of this installation is writing the controller, and that controller is written in a file that has a very unique extension YAML, Y-A-M-L. Controller is defined inside of this file, in which we define the joints of our robot, then the type and frequency at which we want to publish, and command interfaces and state interfaces. These are the things that we will be dealing with when we are defining a controller. It is not very complex, it's just one script, and it is going to make our robot install a controller. The second thing is to be done inside of a URDF. You might have forgotten about URDF, but URDF still plays a very important role. ROS control tags are going to be used, like simple inertia and collision tag that we use while building the URDF. These control tags are going to contain a lot of properties for our controllers, include the YAML file, define the joints, and command interfaces and state interfaces are going to be defined inside of these control tags, and that is going to be implemented in the URDF. The last part is what I call the most important one, and it is of the launch file. Launch file contains very essential things. We need a controller manager, as we have discussed in the architecture of this ROS2 control. We need a controller manager to be launched, we need URDF to be launched, and we need the controllers from the YAML to be launched, YAML files that first created. So all of these 3 things are very essential and necessity to make a controller work on your robot. So this is the process we are going to follow, and let's take a look how we are going to do it. Practically, we understood how controllers work in real time and with works and connection with Gazebo and ROS. How things are going to work, let's take a look. We talked about 3 different files that we need. The first one was the config file, this controller containing script, and that is it. It is a simple script, as I've told you, that is just going to contain the joints that it needs to actuate, the command and state interfaces, the joint state broadcaster, and joint trajectory controller. The type of the controller we will be dealing with, joint trajectory controller. These are certain parameters provided by the wiki that we have set: publishing rate and action monitor rate and stop velocity tolerance and all that stuff. This is provided by the wiki of ROS2 control. So this is the controller. The second thing that we talked about was addition into the URDF. I made all of the changes for you, and we are just going to discuss what the changes are, because I think it would be useless if I start writing in front of you and you're looking at me and I'm writing the code. So the important point here is code is provided in the wiki of ROS. We just need to understand and integrate it. Okay. So in URDF, this is the point where joint 5 ended. And after that, we need to tell our URDF that we are going to have a hardware interface. And that's the requirement of ROS control. So Gazebo tag controls ROS2 Gazebo. This is going to add a library for ROS2 control, and it is going to be using simulation type of Gazebo. And the important point here is you need to provide path to your controller file. In our case, our file was placed in config folder JTC, and it was placed in Big Bazoo package, source folder, workspace, and my address. So if you run this file, it is not going to work. Why? Because I have provided absolute path in my system. Lukman is also included. So you need to change it accordingly to your system. So first we have defined the controller path into UIDF. Then comes the ROS2 control tag, which defines the type of interface we want to have with the joints in the UIDF. Gazebo system, basic syntax, hardware, and joint 1, joint 2, and joint 4. Just these three joints form the whole UIDF, which contains joint 5, baselink, and world as well. But the actuated one are joint 1, 2, and 4. So we are just considering those and installing controller on them. So now our robot can move with these joints. Now you might be noticing that we are just having a command interface of position, and that's what our intentions are. We just need position, joint trajectory controller to work on our robot. We can change it, and I push you to make changes into the state and command interface from joint, from position to velocity and effort and acceleration. So only position interface is given. Parameters for minimum and maximum for the positions are provided. Command and state interfaces are given within initial values. This is the minimum and the least of what you have to provide as an interface for your joints to the controller. Okay, so the second thing has been done. First was controller file, the script. The second was changes or addition of ROS2 control into your UIDF. The third one was launch file. Launch file is going to be very much similar to our previous launch file of Gazebo. It is going to contain the UIDF path. The two new things are going to be first the controller files path, as the controller is made inside of a folder that is inside of a package. So if you remember, if we want to give the path to this file in a package, we need to give an address into the setup.py file. Setup.py file is going to copy all of these folders and corresponding files into the share directory. Okay, now we are saying in the Big Bazoo package share folder, we have a folder name as config, and jtc.yaml is placed inside of it, which is inside of the config folder. We copied it to the share folder. Now controller is accessible. We open up Gazebo and ROS communication, spawn the robot, run the robot state publisher. These three nodes are the new nodes that we have to talk about. First one is the controller manager. As we have seen the architecture, we need a controller manager to load and upload all of the commands from the controllers to the hardware interface. Even the hardware interface is fake or real robot. Controller manager is executed with the required parameters it needs. The ROS2 control node is executed basically. In controller manager, when it is running, we need to spawn the controllers. Now this is upon us. There can be multiple controllers. We just need to spawn two major controllers that are running in this time. That's what our intention is. We can be running multiple controllers, but we do not utilize them, so we do not spawn them. Joint state broadcaster and joint trajectory controller. If we take a look on the controller script, you can see we have this joint state broadcaster and joint trajectory controller. These two controllers are spawned inside of the simulation to act. And let's take a look how things are working. We need to go inside of our workspace, perform call control because we have made a lot of changes. And that's ready. Now ROS2, launch, name of the package, and the name of launch file we want to execute. There will be multiple lines of code running, showing you updates and stuff like that. It is not running Gazebo. Why? There might be some sort of problem. Let me close it and check if Gazebo is working. It seems to be working. I need to confirm that there is no previous execution of Gazebo happening. So I'll go inside of the workspace to perform call convert. If needed, let's run it again and see if it runs Gazebo or not. So the Gazebo was executed inside previously because of any execution that I ran earlier. Now you have to take a look if there is an error or not. The new thing happened here is this number of lines, which added joint 1 position control, joint 2 position control, and state position control, joint 4 position control. So now we can see that our controllers are uploaded into our server, the ROS2 control server, let's say. It has loaded this jtc.yml file and started the controller. Coming back to the lines at the end, we have joint state broadcaster loaded. We have the joint trajectory controller. It has been configured and loaded. So our controllers are loaded. Let's take a look onto our robot. We can see there is some sort of serious problem. But before that, I want to tell you one thing. If there are a lot of errors while running this control.launch file, there might be some required installations you have to do. For example, ROS2, sudo apt get install ROS Foxy joint state broadcaster. You need to install the broadcaster. Then you need to install joint trajectory controller. You need this one as well. And last but not least, controller manager. Joint controller, no, it's just controller manager. You need to install these basic three things, which are very essential to run everything because we are utilizing them in our launch files. Now coming to the point, why our robot has been split up. Let's take a look. We will close it and analyze it from the point where it started to break. Okay, this is a Gazebo related problem, by the way. So I will run it, and this time I will take a look in a close up to our robot. So okay, the joints are falling down, and because of the forces applied to the joints, and then this happens, a very serious problem. We need to solve it, and the solution is very simple. We need to add some friction inside of the joints for the robot. Okay, so we will go to each single joint, and we are going to add dynamics, add a damping of 10 and a friction of 2. It's a random value I'm giving. It's just going to give power to my joints. Okay, friction to my joints. So I'll copy and paste it into all of the joints for my robot. And the last one, link number 1, I think it's saved. Let's perform call and build because changes have been made in the UIDF, and again launch our robot. Let's see if these changes made any progress to the robot or not. So now you can see the robot is not falling apart if we zoom in a lot, and our robot seems to be working fine. So our robot is here in the simulation, and with the help of controller.launch.py file, there is some slight changes in the robot. I will show you what they are. I have tried to add some colors to the robot. We need to check if the controller is working or not. ROS2 topic list. And here we have the joint trajectory controller topic available to us to have a communication and make the robot move. What we are now going to do is to create a file, a node that is going to communicate with the joint trajectory controller and make the robot move. Okay. So Big Bazoo, here we have init.py. We need to create a file. I'm going to say controller test.py. Here I'm going to paste a template of joint trajectory controller communication script. This is a node that is following object-oriented practices, and it requires three things: the joint trajectory controller name and title, which we can obtain from this point, ROS topic to list. I'm going to copy it and paste it here. So it tells the node, the script, that we need to communicate with the controller on this specific topic. There can be multiple namespaces. So specific topic we want to talk, as we have obtained from ROS topic list for our robot. The second thing is, what are the joints for our robot? And as we know, we have joint 1, then we have joint 2, and joint number 4. If you don't know where to get these joints, go into your controller that you have made. These joints which are inside of the controller are the joints that we need to talk. And what positions do we need to send to our robot? Joint number 1, I want it to send 1.57. A float value is a must here. And to joint number 2, I want to send 0.59. Random values I'm just giving 1.2 to joint number 4. So it just takes the topic of the joint trajectory controller, number and name of joints, then the position that you want to send to the joint trajectory controller, the joint specifically. All of these values correspond to these joints. Now this node has been created. How does the system know that this node exists? We need to tell it inside of the setup.py file when we are dealing with Python nodes. There is a specific syntax when we are providing the Python node to be made an executable. So trajectory message is going to be the name through which we will be calling it. Okay. And what is the name of the package? Big Bazoo. And what is the name of the file? Controller test. This is a syntax that we have to follow, and the function that we need to directly call is the main function. And to make this file accessible, we need to perform call can build. This is a process that might scare you off, but you are going to do it a lot in the upcoming section, so don't get afraid. It is going to become your muscle memory. Let's see our robot. It is still there. ROS2 run, and the name of the package in which the node is placed. I'm going to double tap the tab button, and we can see we have a trajectory message that we just gave the name. And let's press enter and see if our robot executes the trajectories or not. There seems to be some sort of problem with the robot, and it is not executing the trajectory. That can be a reason, in possibly because of some naming convention issues. The names of the joints are not correct, or can be the title of the robot, title of the topic on which we are communicating. So there can be many reasons. I want you to debug it. This is the basic template, and I want you to make changes into this and solve this problem and make your robot move. From programming perspective, there is nothing new that you have to do, or everything is done. Okay, so stop this video right now and make changes into these scripts and make the robot move according to the commands that you have sent. Some changes in the color of our so-called by Big Bazoo, and now I am going to make the trajectories perform the way they should have been. Controller and minus 1.5. I'm just giving some random values to the joints to see an effect. Now changes have been made, so performing call can build in our workspace, and we are now going to look closely to the effect of the trajectory that we are sending. So you can see our robot is performing multiple trajectories. We just need to change these values, and our robot is going to perform those trajectories. Again, I'm going to perform call can build and run it. So the problem was related to Gazebo, and I have added some colors to the robot, and trajectories are working. A controller has been installed, and our robot is working perfectly fine. If we take a look into the changes for the color, are these simple changes: Gazebo reference base link, Gazebo link 1, link 2, link 3. All of the links are given a reference, and the colors are applied from the Gazebo library. And you can see this trajectory controller is working perfectly fine with this controller test, and things are working. Our robot is moving according to the trajectories or positions that we are sending. So that's it for this Big Bazoo. From now on, we are going to work on a very serious robot and make it move and do awesome stuff and learn a lot. Let's jump into KUKA robot. KR 152 or any other, but it's a 6 degrees of freedom robotic arm. We have been working with our custom robotic arm, which was very funny as compared to this one, the real thing. There are going to be a lot of things we have to do. We are going to get its package from GitHub, but the point is, it is not going to be a straightforward execution because KUKA has not provided its support for ROS-based Gazebo models for ROS2. And it was previously for ROS1, but we are going to convert things and make it work for a ROS2 installation. And that's what is the point we are going to learn. Now, first we need to understand what this whole Gazebo available KUKA-based package it is all about. We need to understand how you can utilize the already available robot packages into your simulation, because you can see this robot is a real-world robot and it performs all of the things it can. Apparently, it has 6 degrees of freedom, meaning 1 at this point, 2nd at this one, 3rd at this point, 4th this, 5th, 6th. Axis for this rotation, then this rotation. At this axis it is rotating. This one is rotating, I guess, along this direction, and this one is again rotating along this direction. I don't know, but you get the idea. There are 6 joints that are going to be rotating at different axes. So it is going to be able to grab the things as well. You can see there is a gripper as well, which is a very solid one, and we can grab things. Before that, we need to solve inverse kinematics, and that's what we are going to learn. Let's jump into the obtaining of this package and setting it up for our workspace and ourselves to use this robot. Let's take a look. What I showed you in the question is KUKA KR210, and it will be going to have a claw as well. The main files are obtained from this Udacity RoboND Kinematics project. It is an open source project, and it is actually a repository provided to the students of Udacity Robotic Software Engineering. So we are going to obtain robot from them, and we will process them as we like. Although, if you want to know more about the robot that we are going to work, it is going to be obtained from an official ROS Industrial KUKA experiment repository, where siblings of these robots are also present. You can test it, see it, and process it the way we are going to do it. Okay, there is not an authority or a specific robot of Udacity. It is also obtained from KUKA ROS Industrial provided repository. Okay, so we will download this repository by copying it and copying the link, going into the terminal. In the home folder, I will be performing git clone, and it is going to clone it, or I already have it, so it is saying that you already have it, so don't create it again. Now what I'm going to do is going to create another package for this thing, and if you have forgotten, I'm going to copy this command. Now this one is for CMake, for C, and I am interested in Python. Okay, copy this command, and I am going to name the package to be KUKA KR210 ARM. Okay, that is going to be the name of the package we are going to be dealing with from now onwards. Pressing enter, I am in my workspace source folder. This is important. Okay, package has been created. If I go inside of the package, I am going to create some folders: launch folder, meshes folder. No, I don't need the meshes folder. Config folder and URDF folder. I think I don't need the URDF folder as well. Okay, launch, config, URDF. I think that's enough. So they are created. Open up your Visual Studio Code, and here I'm going to add a folder, and it is already showing me this folder here. I'm going to add it. Yes, I trust this folder because I created. So we have these two packages in our workspace source folder, and we have added them into our Visual Studio Code. I'm also going to add the folder that we just downloaded, the kinematics, the Udacity NanoDegree repository, because we are going to obtain a lot of things from it. We need the config folder. I think we don't need it right now. The Udacity repository is based in ROS1, because I can show you, if I open up this launch file, you can see with the syntax it is based on ROS1. It is not going to directly work on your ROS2 system. Okay, so what I have to do is obtain the files I require, and then I will change things for ROS2. Okay, what I was interested in, if I close this and open my newly created, because I'm going to drag and drop a lot of things, we need the meshes. Meshes are going to be placed inside my package. Yes, I want to move it. Then we have the URDF. URDF folder is already created, so I just need to select them and drag them to the URDF, move them. URDF is done, meshes are done. What are the models? Models are not required. Scripts, no. Include files, no. Launch files, we'll create our own launch files. Config contains the controller. And you can see this is old implementation of joint trajectory and position controller. We will do our own for educational purposes. I think that's enough. Now we have the URDF, we have the meshes. We need to process that, and then we will move towards changing things for ROS2. Okay. If we take a look into the URDF, URDF is including a lot of things, and it might be a little bit complex because it is a Shakro file, or Zacro, whatever you want to call it, as it uses placeholders for values inside of it. We need to make it simpler, as it is a beginner's robotic arm course. I will convert it into a single URDF file. All of these three files will be converted into a single URDF file, and then we will utilize it in different manner. But first, we need to perform a lot of things, and that are related to the share folder. I am going to be needing one interesting thing, and that is this path. If I open up the setup file for this package, I would be first need to add the launch file, launch folder into my share folder of this package. And yes, these libraries as well. When they're done, this launch folder, a meshes folder, what else is there? Meshes contain two different folders. Okay, that is going to be a little bit complex. We have a URDF folder, URDF, and to make things easy here, I am going to bring all of the gripper things into the. Okay, we have two options. We can create multiple folders inside of the share folder, or we can bring everything inside of one folder. Things are going to then get very easy for us. So we will follow that one. Okay, we can create multiple folders as well, but we are not going to do that. All of them are different. The collision are STL, and the base visual are DAE Collada file. So I'm going to bring everything into this. I think I should not do that. The collision file should be inside of the collision, and these visual things should be inside of visual movement. It is going to be a long process setting up our robot. Okay, so where was the setup file? In setup file, I am going to perform another interesting part, which is package name of the folder we want to create or copy the files to. So it is basically meshes. In the package KUKA KR210 ARM, there is a folder named as meshes. Gripper is now empty. So meshes, and this folder, let me give it name. I think we don't need this folder now. We just have these two folders, collision and visual. We'll bring them to meshes directly. We don't need this folder as well. So meshes, and there is a collision folder. And what files do we need to copy into this folder? We are going to be needing collision, meshes collision, all of the collision files. Okay, same goes for the visual one. Visual, and copy everything inside of visual. To see the magic, we have to be inside of the share folder. What is actually happening? Robotic arm workspace install. The folder is not yet created. Okay, that is interesting. I think everything is fine. Let's perform colcan build to see if things are working or not. Colcan, no, inside of the workspace root directory, which is this one. Colcan build. Let's see if it processes it or not. It has processed it. So now we have in the install folder of our workspace, we have KUKA ARM. In the share folder, we have KUKA ARM, and let's see if things are perfectly copied or not. In meshes, we have two folders like this here, collision, all of the collision files, and all of the visual file, the DAE. What we are doing is making things accessible to the system so we can produce a URDF. I know it is a little bit confusing, but you have to go through this process to make robot models work for you. Now we are going to convert the Zacros into URDF. It is not a direct process. We have to go through a lot of things and understand how system takes a look into URDF. Okay, so let's start performing the exploration part. I'm going to paste a command here, which is going to be dealing with a lot of things. I'll tell you later. Now, in this main file, there is a target URDF, which is a small one. There is a gazebo file, which contains gazebo related stuff, and a URDF Zacro. URDF Zacro KR210 is the main file here. Okay, so I will be looking into it. Does it contain the claw or the gripper? It contains the gripper. Yes, I was finding it. So what we need to do to make this Zacro be converted into URDF correctly, we have to provide a absolute, not the absolute part, the correct path. Okay, so you can see it says find this path, and in this path we have this. In our case, things are different. We have a different name for the package. You can see. So we are going to give it the name that our package is having. Okay, so find wherever this is in KUKA ARM, wherever this is, replace it with the name of the package we have. Okay, now it has been changed. Okay, first thing has been done. We are now trying to provide exact and correct paths to the files that are present in the share folder. We are converting ROS2 based URDF Zacro into ROS1 based into ROS2. Although it is not required, but I'm doing it for you so you can play with the Zacro files available on the internet. Coming to the point, when we have this file, we go into the URDF, and then there this is present. Is that correct? In our package in URDF, KR210 gazebo Zacro is present. Yes, that is present. Coming to the meshes, this is going to take a lot of time because meshes are involved and we have to be very careful when dealing with it because we deleted a lot of folders, right? So wherever the package is KUKA, go into the meshes and in this folder. In our case, in visual, if you want to reach visual, we just go into meshes and then visual. So this folder has been deleted. We are going to select it, Control F, which is going to bring in all of these matching things. I need to replace it with just meshes. Okay. And it has replaced for 14 different things. So let's take the path, our package, KUKA, and then meshes folder, yes, and the visual folder, then this based link.da. Here it is. So path has been corrected. Okay. Coming to the collision part, and in collision meshes, collision base STL path has been set. Let's move to the next thing. If we have corrected everything automatically, yes, seems like it. The collision and visual paths are now fine. The package name, the folder, and the path to the specific file is corrected. You can see this is the basic way of converting a file into what. If you have changed the name of the package or the location of the files, you need to do this. Now you can see all what benefit we get for using this file. All of the values, inertial and collision, and all of the serious computation has already been done. So coming to the gripper. Now in gripper, things are different as we have placed the gripper files as well in visual and collision. So we have to provide the path to it, the correct one. In KUKA, in our package, meshes folder, there is a gripper folder. No, there is not because we have already deleted it. And gripper base.dae. For both of them, the same path. For collision and visual, same path. Where is it? Gripper base.dae. It is present in the visual. So we will see in meshes, go into the visual and you can find it. Again, finger right.dae. Finger right.dae. Go into the visual and here you can find it. In this collision file, you can find it in collision. So you see that you need to understand what actually is written inside of a URDF. That's why I made the first robot. So you can make changes into it. I think other than that, everything is fine. No, it is not fine. It is a ROS1 based file, so we have to delete these transmissions. We don't need these transmissions. For these transmissions, now we utilize ROS2 control tags, and we don't need these transmissions. I'm doing in front of you, so you should also understand how you can do the same stuff. Okay, nothing seems to be fine. Let's open up the next files. This one is done. Let's go into the gazebo, the related file. In gazebo, reference links are, is there any link added into the robot? ROS2 control is added, although I think it is not required. Grass fix, that's fine. No path has been given, so it does not affect us. Same goes for this one. Okay, now coming to the point that our files are ready. We just need to convert the files into a URDF, simple URDF, so we can visualize it. I'm going to open up this folder where this file is placed, KR210 URDF Zacro. Why I am doing this? We need all of these three files because they are imported in one of each other. So we need to convert into URDF, which is basically going to copy all of them and replace all of the placeholders and provide the values. So the command is, I'm going to fix it a little bit. What is the name of the Zacro file? Zacro file ROS2. If you don't have it, you need to install this thing. Sudo apt get install ROS Foxy Zacro, which is a required package for ROS. Now we need to perform the conversion using this specific package ROS2. Run. Name of the package is Zacro and Zacro 2 times Zacro. Then let me follow the syntax. Name of the Zacro in order and this thing. Okay. Name of the Zacro KR210 dot what is the name of the Zacro exactly? URDF.Zacro and in order. Then this sign convert into KR210.URDF. Let's take a look what happens. So it seems like it has done the thing. Let me take a look. If we take a look into this URDF folder, we can see that KR210.URDF has been produced. Let's open it. So it says this document was automatically generated, auto-generated by Zacro, and we can see these are the contents of Gazebo, the first file that was imported. And I would not be needing this control plugin, grass plugin, that's fine. And then the file starts here, the importing of the visual tags and all of that stuff. Important point here is all of this has been generated. If the paths were wrong, it would not have been generated. Okay, so we have to fix the paths first. The system should find the paths. And to me, things are working fine, and we don't need other three files now. This only one file is enough. Now what I'm going to do is obviously launch this robot and see how does it looks like. Now I am going to copy these three files from my big Bazo and going to paste it inside of this folder. First, RViz. It is going to be name of the package. Name of the package. The URDF file is going to be KR210, and else everything is going to be the same. For Gazebo, the file is this, name of the package for Gazebo is this, and rest is everything same. So we need to, in the setup file, did we perform launch, and yes, we provided the configuration part to be copied into share folder. Okay, now we need to perform call can build and see our robot. Moment of truth, if it works or not. ROS2 launch. What was the name of the package? KUKA KR20, okay, and Arvis. Robot state publisher and joint state publisher is also going to be launched. It seems to be working fine. Whoa, we have a lot of big thing which is totally white. The reason is, what is the name of the fixed frame in this UIDF? We have to set it to be fixed for the first thing. It's base footprint. If you take a look into Arvis, let me bring it up. It is base footprint. Let me select it, and here we have our robot, a huge robot by the way. And if I bring this joint state publisher GUI, we have a lot of things. Let's play with them. Joint 1. Okay, limits are also applied. Joint number 2, joint 3, joint 4, 5, and joint number 6. These fingers are also working, right? Yes, the fingers are also working. So our robot is working. We have successfully converted the Zacro files obtained from an online package and converted it into a UIDF for our easiness, one single file, and it is working according to the visual results we have seen. In the next lectures, we are going to convert it for the Gazebo and install a controller into it. So previously what we did was interesting. We downloaded the package, converted it into a form that it can be executable or runnable on ROS2, then brought it into Arvis2. One step has been done. Robot has been made to come into a simulation, and it's working. It was working. Joint X's were working in Arvis. We tested it. Now is a task that is more complex than the previous one, and we have to bring our robot in a working state in Gazebo. So let's start it. I have copied all the launch files from the previous package, so we don't need to write them again. We need to just do one small change, and that is name of the package to get the share folder, and then UIDF and KR210 is the same process, the same structure that I always follow. File is placed in the UIDF. I'm going to make a small change. I'm going to create a copy of it, and I'm going to name it to be the same but with a dash at the end. Why? I will tell you now. So Gazebo is going to access this thing, and Gazebo is going to this launch file is first going to launch the ROS Gazebo communication, then spawn this robot and with this name and robot state publisher. Simple, isn't it? Let's run it and see what does it performs. We are going to go inside of our workspace, perform call can build because changes are made. A new UIDF has been made. ROS2, launch, KUKA, and Gazebo. So let's take a look. How does it look like? It was working on Arvis, right? But it might not work on Gazebo because of a lot of reasons. Let's first understand the reason. Let's take a look. So spawn entity has successfully spawned it. Okay, but output is not showing on the screen. Gazebo is causing some problems. We are going to close Gazebo in a perfect manner, and then we will run that again. Now let's run it again and see the output, if the robot is shown or not. So Gazebo is causing some problems. The main reason is Gazebo is unable to find the package models or meshes. If we open up this UIDF, we can see we have these package KUKA, KR20, R meshes collision and all that stuff, but Gazebo is unable to find them. One workaround is to copy all of these meshes and paste it into Gazebo mesh folder. If I go into my home folder and first I need to copy all of the meshes, and these are the meshes. Let me copy the whole folder and then go into the home folder, Control H. You might observe Gazebo.gazebo, and in Gazebo we have some models. I am going to paste my models here, and I am going to delete all the file except meshes. So now Gazebo understand the path through this. KUKA, KR2, meshes, collision, all are pasted inside of Gazebo model directly, and we don't need to give paths to this. Okay, so let me close it. I'll open it up again. Go into this. What I am assuming that Gazebo was not turning on because of the paths error. Okay, so let's take a look if that is solved or not. And to some extent, yes, it is solved. Gazebo is now being able to find your robot model when accessed through this package stuff. This package, KUKA, KR210, and meshes collision, all of the meshes with this name are pasted into Gazebo models. But that is not a good solution. I will provide you a proper solution in which you don't need to have to perform this copy pasting of the models. Okay, let me just delete this file again. I don't know why I created it, and I'm going to remove this dash. And we can see the important point coming to the thing that we need to learn. Our robot has been sort of dead. If I bring it up and see if it moves or not, no, the robot is actually fallen on the ground because of the gravity, and we need to solve it by installing controllers. But to this video, to this lecture, we just need to understand one concept, and that is to make the things work in Gazebo, we need to provide absolute paths. Absolute path, we can directly go to this meshes folder, copy the path, and provide it. But it will run. But the problem here is Lukman is inside of this path, which means it is only going to run on my system. The thing that we did, copied and pasted in meshes of Gazebo, things are going to work on your system by doing the same thing. And interesting thing, if I just open up Gazebo, I don't run any launch files, and I go into this insert, you can see in the .gazebo, if I make it big, models, I have, where is it? It is not showing right here because UIDF or SDF is not there, but it will appear here if we create a small SDF. Meshes are present here. We can bring them here, like these models I have already made, and Gazebo can easily access them. So problem solved. Okay. Now what I'm going to do is make the robot stand still in the next lecture through controllers, the way we did it with the basic Big Bazoo. And all of the things that we know, we have the robot there. It is working with different joint states, and we can see it is awesomely integrated with our ROS system and in our workspace. The next thing that we need to do is to take care of its motion. because that's the main reason of a robotic arm. We can control it. For the controlling part, we need controllers, right? And ROS controls are going to be helping us in that. Now, the point that I want to teach you here is how you can bring in a robot, add controllers to it, and use it for your simulation. Controllers are going to be the main point here. So first, we need to define what type of controller we need to integrate it with this robot. What I have come up with is joint trajectory controller. Obviously, for starting out, that joint trajectory controller is awesome because it is very simple to integrate and it provides us with huge functionality. We just tell the robot to move from point A to point B and it automatically generates a smooth spline, right? That's the power of joint trajectory controller, position specifically. So it is going to be joint trajectory controller, interface decided. So what was the process if you don't remember it? First, we need to create a YAML file that you can see right here. Then we need to install ROS2 tags inside of our robotic arm. It was containing ROS2 tags, but for ROS1. In ROS2 things are different, so we have to install it by the new syntax that I know, so I will install it and you will learn from it. Then the control manager login. This was the three-step process to install a custom controller or any other controller into your predefined controller into your robot. This YAML file is very much similar, right? But things are going to be different because gripper is also involved. Joint state broadcaster, the common one, joint trajectory controller is defined, joint trajectory controller, and joint trajectory controller is its type. It is going to be dealing with position of it. The joints are involved are 6 joints of our robotic arm. The 2 new joints that we will be adding inside of it are left and right gripper fingers. And command and state positions. Command and state interfaces are going to be dealing with just position. No velocity, no effort, no acceleration. Important point here is our gripper is not going to be that much awesome of a gripper because of a reason that it is just a position controller for the gripper. If you want to make a gripper strong enough, you have to add an effort controller into this YAML file so your gripper can work properly. Okay, so let's take a look how we are going to practically implement a controller inside of our KUKA robot. Let's take a look. Our robot was fallen on the ground. We need to take it up and make it work, right? How we are going to do that? We just need 2 simple things. The controller file and the control manager to launch it and the UIDF as well. So let's start the process. First, we'll go into the launch file that we created for Big Bazoo. We need to do some changes inside of it and then we will move towards the UIDF part. What is the name of the UIDF we are using right now? KR210. So KR210 is the file, UIDF file, the package is this, and all other things seem to be fine. In config folder, we are not using the JDC right now, so we are going to copy it and bring it here. From Big Bazoo to KUKA package. Okay, here we need to do a lot of changes as the robot is different, joint names are different. The next thing we need to do related to the configure file, where it is, sorry, the launch file. First second, Gazebo is launching, spawn it with this entity name, robot state publisher, controller manager, broadcaster, and project. Everything seems to be fine. This is the easiness of creating a package and then utilizing all of its resources again and again because the basic structure is the same, just the UIDF changes. Now, launch file is ready. Okay. Coming to the UIDF file, we'll look into it. First, we need to make some changes here. I already added the configure file name, copy all of the contents of this config folder and get them into the share folder of our package. Why do we need it? Because here, the controller file has been accessed through the share folder. It is placed inside of the config folder of the directory we are using, and GDC is the file that we are accessing. And it is being accessed by the controller manager. So the setup.py file and this line specifically is very essential to load the parameters. Now, UIDF, the main part here. If we go up here, as I know about that, as I know about the UIDF, as I know about the UIDF where all of the files and things are, I'm going to bring this ROS control plugin, which is an old implementation, into this file. ROS1 implementation, I'll delete that and I will add the new one, ROS2 based, ROS2 control based addition required for the control stack of ROS. Okay, so UIDF from Big Bazoo is what we are going to utilize, and we will copy all of the contents from here, and we are going to paste them. We can paste them, but I think I already did it, so let's take a look. If we go, huge UIDF of KUKA, and if I uncomment it, the first thing is to enable the libros Gazebo plugin, this one. So I will add this one as it was not added, and the package is different, by the way. So we are going to copy the path and provide the path to this ROS2 control plugin that we are activating, which is of KUKA KR210, not the Big Bazoo. Okay, we are going to make some changes in that as well. It is not made for KUKA right now. Now this thing has been done, library is done, and Gazebo system, it is totally the same. Everything is ROS2 control. This is essential. Now coming to the point, joint 1, joint 2, joint 3, joint 4, and I have made changes inside of all of this before this video, obviously, and I have used the command interface to be position and state interface to be position, velocity, effort, whatever you want. But I will be using just the position joint trajectory controller. Okay, that is very similar to this, although one major difference, the state interface is position here. That's not a big deal. We will be utilizing just the position interface. You can before you, I have written this velocity and effort as well. Now, all of the joints which are actuated are written here, and the interface has been provided. So left gripper finger joint and right gripper finger joint is also present inside of our interface for the controller. So UIDF changes have been made which are essential for interfacing for the controller, and now we need to make changes into this controller file. What were the joint 1 to joint 6? From joint 1 to joint 6. Joint 1 to joint 6. All of them are actuated. And joint 1, 2, 3, 4, 5, 6. Then comes the next things, which were right gripper joint and left gripper joint. The fingers of the robot, they are also actuated as prismatic joints. I will show you. But first, we need to set the controller and everything related to it so our robot can stand properly. Okay. Currently, we are just installing the controller. 1, 2, 3, 4, 5, 6, and left and right joint controller. So JTC YAML is now set and it is being accessed into the controller file. So to me, everything seems to be on track. And now I am going to perform call can build and then run it to see if our robot is standing the way it should be standing or not. ROS2, launch, KUKA, and this time controller.launch.py file. So let's see if it loads the controller or not. And wow, This time you can see our robot is standing fine in gazebo, which is because of only one reason. Controllers are now set for this specific robot, and we know that before controllers the robot was crumpled and it had been fallen on the ground. So you can see these controller information has been provided for which joint, what command interfaces are provided, what state interfaces are provided. We can utilize them. Okay, so controller file is loaded properly. We need to perform a final check. ROS2 topic list. That is going to tell us all about the available topics, and you can see joint trajectory controller is available to us, so we can make this robot move. That is what we are going to do in the next video. But our robot with the custom controller is now set. Okay, and we just need to make some changes, not the changes, just write the nodes and make this robot move in the upcoming video. Everything is fine. Our robot is now compatible with ROS2, although it was not. So now you have learned that. Now we want to make the robot move, a very basic and essential thing, but you understand the concepts and all of the paths that we have taken to come to this point. It's now time to make this robot move. We are now going to create a node that is going to talk with the controller of our robot, and that's how it is going to move. So in the KUKA package, KR210ARM, I am going to create a Python node, and that is going to be made inside of this folder, which is of the same name of the package, and it contains the init file as well. New file, controller test.py. It is going to be the name of the file, and I am going to create it and paste a lot of contents into it. All of these contents are just generic contents. You can make changes into them. It's basically a template. So you might have seen in the previous robot, Big Bazoo, but I just wanted to give you some explanation that it is a very simple node. It is when so when we execute it, it comes to the main function in which object of this class has been created, and it spins it, and it destroys when Control C or executing kills button is pressed and it shut down. So what is happening inside of it? Trajectory publisher node, and a node is initialized with this name, and this is the topic on which it is communicating. You know where we get this, and it is publishing for every 1 second, and we have to provide joints and goal position, and the robot is going to move. So what are we waiting for? Let's do it. So open up this controller file, because we will be needing it as we need to fill some values into the joints of the robot, right? So let's start it. Joint 1. Let's first write these big joints. No, joint 1 would be good, because we have to maintain the order while giving names. Why it is not moving? 2, 3, 4, 5. Again, I'm making the same mistake. 6. So 6 joints. 6, 5, 4, 3, 2. So these are our joints. Let's add the last 2 joints. And all of our joints are now mentioned in this file. Now we need to give different values to these joints so the robot can show us action on the positions we are going to tell. For all of the values, I'm going to say 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, and 0, 0. All of them should be floated. Okay, 1, 2, 3, 4, 5, 6, and 2 for the end joints of the fingers. Okay, it is going to be executed, so it must be told to the package to make it an executable. Basic ROS2 concepts, and we are going to do that in the setup.py file. We need to tell the package that we have created a node, execute it, or make it an executable. Okay, name of the file is going to be trajectory execute, and it is going to be from the package. Name of the package first we need to tell it, dot name of the file, controller test.py, and the function that we want to call. Main function is going to be executed when we call it. So let's perform the Colkin build and make all of the changes. ROS2 launch and controller.launch. I want the robot to be up and running in the simulation before I run this file. ROS2 run, name of the package, and double tab press. It is going to tell me trajectory execution, the name I told it. I am now going to run it and see if the robot moves or not. So there is some sort of an error in the naming convention here. I have written pi as well. Oh my god. Colkin build. Changes have been made, so that's why Colkin build is essential. Let me make it small, and I'm hoping that it is going to run now and see the robot if it is going to make any action or not. Let's make the robot move and try again if it is going to move or not. So our robot is not moving. What can be the reason? If I perform ROS2 topic test, we can see the controller is not running. Wow. Let me stop the things and rerun it to see if the controller is running or not. Kill all GG server. That's a lot of time I have to perform it. CD, go inside of the workspace, run the robot and the controllers with it. I'm going to now check if the controllers are working or not. ROS2 topic list. Controllers are working. The name of the controllers is exactly the same or not. Joint trajectory controller, joint trajectory. Controller name are fine. ROS2 run, name of the package, and trajectory execution. Let's see if it makes the robot move or not. Okay. Whoa. You saw the fingers also closed, right? So previously when I executed it, controller was not running. I don't know for what reason. I ran the same thing and it is now working. Now I'm going to make changes in the position and see if things are going to look fine or not. I'm not going to change everything, but some of the things, okay? Because if I make a lot of changes, I don't know, I might make the robot collapse, okay? So changes are made. We are going to perform Colkin build and see the effect of the changes. Again, run the same node, but with different values. So you can see our robot is moving. We are providing joint values for every single joint, 6 different robot joint and 2 fingers joints, the prismatic joint. So 8 total values are continuously being published to the controller, and it is making the robot move. You can play with it. You can change these values, and if I give a wrong value, let me show you. Robot will collapse. Things are going to get interesting. I have saved it, perform Colkin build, and I'm going to make it execute. Let's see if it collapses or not. No, it doesn't, but it moved in a very free manner. So our controller is working. That's what we were checking. Next, we are going to be dealing with the kinematics. So first understand what is forward and inverse kinematics, then we will move towards the scripts. With links and joints connected in chain, we need to take care of some serious mathematics. And in the branch of mathematics and statistics, there is a branch known as kinematics. We deal with the motion of a body without considering the force that caused that motion. Okay. Before diving into it, we need to understand what are joint spaces and what are Cartesian spaces. Now, the word spaces is very confusing, right? Spaces basically means an area. Let's say a space, like this is a three-dimensional space in which you can see the object from this angle, from side angle, and from below angle. It is not a 2D space. Now, Cartesian space is a very well-known space. You might not have known it by this name, but it is actually x, y, and z values with the roll picture angles respectively. So whenever we say the end point of this pen or end effector of your robotic arm is 10 in x, 10 in y, and 5 in z. So we give it a location in the xyz Cartesian space. And that's what we want with our robotic arms end effector. We want to give the Cartesian space end effector. So it can relocate its position where it is in the three-dimensional space. Okay, that is Cartesian space. Now what is joint space? Robotic arms joints produce all possible values, all possible its motion in the joint space. Let me give you a better understanding through this example. This is a robotic arm, 2 degrees of freedom robotic arm, which can rotate along the z-axis here, and then it can rotate along the z-axis coming out of the plane. Okay. Now, as it can rotate along both of these z-axis because there are two multiple joints, what are the joint space? Joint space for the second z-axis, z2, are the all possible values this joint number 2 can make along the z2, because as for its space, the joint 2 space is, it can come to this point, this point, this point, this point, and the point where it is. So basically, where all possible joint values are known as joint spaces. We don't want the robot to collide with its body, but all other than colliding are known as joint space possible values. So we take a look into a robot's motion through joint space and Cartesian space. We say the 30-degree robotic arm joint 2 value is going to produce this position of our link number 2, this one. So this is in the joint space. In Cartesian space, if we define the same thing, we say that link number 2 is now pointing to 4 of x, 8 of y, and 2 of z. So this is going to be Cartesian. But 30-degree is going to be, or it can be in Cartesian, but we will make it more joint related thing. Okay, so that's joint space and Cartesian space, a very essential thing when working with robots. Coming to the topic of kinematics, forward and inverse. In our case, things are going to be very easy because we are going to just utilize this line of code, and it will read the UIDF file, and it is going to produce the forward kinematics and inverse kinematics for our robot. This library ikpy.chain is going to produce the forward kinematics and inverse kinematics solution for our robot. We do not need to do anything. Okay, that's why I have utilized this one library. Now coming to the point of understanding of forward kinematics. What is forward kinematics? Forward kinematics is a basic computation of the end effector. This point right here, known as end effector, which is at the end of a robotic chain. We just provide the values of Q1, Q2, Q4. Let's perform an example. 20 degrees of Q2, 30 degrees of Q3, and 40 degrees of Q4 is going to produce the end effector position in Cartesian space to be 10, 20, and 4. 10 in x, 20 in y, and 4 in z. This is known as forward kinematics. We give the joint angles in the joint space, and it produces the end effector value in Cartesian space, or a place where end effector is going to be. We know where the robot's end effector is right now because of these angles that we provided to the joints. This is known as forward kinematics. Coming to the inverse kinematics, which is basically an opposite wave, which is basically opposite to what is forward kinematics. We provide 20, 10, and 8. We provide the Cartesian space values in XYZ, and it automatically produces all of the values for theta 4, theta 3, and theta 2, and theta 1. So what is forward and inverse kinematics? Forward kinematics produces values, and there is inverse kinematics, which also produces value, but there is a difference. It moves to Cartesian space, and inverse kinematics produce, and it moves its values to joint space. So in inverse kinematics, which is more computationally complex and hard to find because there are multiple possible values for the robots to reach a specific point. Robot can reach the specified end effector from this angle as well, from this angle as well, from this angle as well. So there can be multiple positions to reach a specific end effector. Inverse kinematics is the hard thing. But it is more real world. We cannot tell the robot again and again about move your first angle 10 degree, move your third angle to 20 degree, and then you will reach that point. That's not feasible. Inverse kinematics is feasible. We just tell, take your joint angles from your inverse kinematic solution, just make the end effector point to reach point 10 of x, y, 20, and 30 in z. Just reach that point. I don't want to care about all of the joints because in redundant robots, we have more than 6 degrees of freedom robot. So we just tell x, y, z, and that's what we would like to have. So let's take a look how we will implement this in our robot. Controllers are installed. Model is working fine in Gazebo and Arviz. What's next? Make it move according to the requirement. And that is the next question, right? So we are going to solve this question through inverse kinematic solution library that we are using iKind.py. iKind is not the rule of the thumb using library because there are a lot of libraries available to solve the inverse kinematics solution trajectory generation. I am using this one for this course. In previous courses, I was using robotics toolbox for Peter by PeterCode for Python. In this one, I am using this new library because it was very easy and it can easily read a URDF. So how we are going to do that? We are just going to provide the URDF of our robotic arm, KUKA, and supply it into this library, and it is going to generate the transforms that are required for the DH table, inverse kinematics, and all of the stuff can be generated easily with this library. So the important points in solving a kinematics for a robotic arm or robot is transformation matrix. The second thing is, after obtaining the forward and inverse kinematic solution, you pre-process the output of your library. In our case, because of the fixed joints in our robotic arm, we are going to face some problems. Fixed joint here and fixed joint here, they are going to be producing 0.0 value for these fixed joints. All other joints are going to have a certain value, 2.7, 3.8, 6.4, but the fixed joints are going to be producing a 0 value. We have to delete it with some Python programming skills. And when they are removed, only joints which are valuable to the motion of a robot are going to be staying there, and we will implement and send it to a joint trajectory controller to make our robot move. It is going to be a lot. Let's jump into our robotic arm and see how does it looks like. The library I'm going to be using is IKPy, Inverse Kinematics by this Philiad. Awesome person who maintained it and has been building with the help of these contributors to this date. Now, this library requires just the DH table or a URDF of a robot, and it can produce inverse kinematic and forward kinematic solution very accurate. We will test it in this lecture. So in this library, you can see a lot of documentation is also provided. Simply, you just need to copy it and paste it here, and you can easily install it like the way I did pip 3 install IKPy. I've already installed it for Python 3. You can also install the plot, and other options are also available to build it from source. So this library is going to make our life a lot easier. And why should we do the things that are already done, and awesome people have done that already? So we need to first understand the interfacing of this library, right? So I have written this kinematic solver.py. This is a script that is going to give us the interface information about our robot and the library. So what is happening here? First, we import the library, the method that we want to access the chain, NumPy and OS as well. Why OS? Because it is placed inside of this folder, which is the module, Python module, and it is going to need the access to KR210 URDF file. So we are using the Python OS library to get the path of the URDF folder and KR20. If you use the same structure of the package by downloading it from the repository, I will be providing the link. It is going to be working. It is not going to contain the absolute path, so it is going to be working on your system as well. The URDF and this URDF is going to be read. Then we supply this URDF file into this library, which is going to produce us the forward kinematic solution and inverse kinematic solution. Let me run it and then I will show you. This is not going to be run under ROS hood, okay? It is going to be executed independently as a Python script. So when you will run it, there are going to be a lot of things printed on the screen. Don't care about them. They are warnings. They are not errors, okay? They are telling you about some of the joints and links are fixed and they are causing problems. So transformation matrix is produced. Transformation matrix is very essential when we are dealing with kinematics of a robot because it tells us about the rotational and translation part of the robot. Now, transformation matrix is produced for all of the angles to be set to 0 degree. Okay, you can change the value. It is saying the forward kinematics produce the forward kinematics or produce a transformation matrix for the robot end effector from base to end effector by giving 9 values to be equal to 0. So it has somehow produced 9 joints or 9 angles on which this robot has been constructed, although there are 8, but some sort of problem. We will solve that. That's what this interfacing is all about. So 9 0 degree values are provided to all of the joints that the robot contains, and then the transformation matrix is produced. Transformation matrix provides us very serious information. There is no rotation right now, identity rotation matrix, but for the translation part, you can see it is 2.3 meters in x-axis and almost 0 in the y and 1.946 in the z-axis. Is it correct or not? We'll check it. We'll testify this library with our robot. Okay. Now the next thing is we are then going to provide a 3-dimensional point. All of the values are 3-dimensional values x, y, z. I'm going to say 2.2 in x, 1.2 in y, and 1.2 in z. A point in 3D space, and I want the robot's end effector to move at that point. Then tell me the joint angles the robot is going to have. The inverse kinematic theory that we discussed earlier. So it provides us all of the joint angles that are required to reach this point in a 3-dimensional space. This is an important point because we are going to be using this concept in our robot a lot. So it produced 9 joint angles because it is understanding that there are 9 different joint angles for our robot, and these joint angles are provided. If we give these joint angles to our robot through the interfacing of the joint trajectory controller, our robot's end effector is going to be at this point, at specifically this point. This is what this library is claiming, implementing the inverse kinematics. Now we have to fine tune the results because there are some zeros in the joint angles, and we don't want the last 2 joint angles, which are of the fingers. We don't need specific angles for them. We know there can be 2 positions only which are useful. It can be open, it can be closed. Okay, so we are not performing the grabbing of an object. That's why we don't really much care about the fingers. So we will delete unnecessary angles with the help of this command and the NumPy. We are going to delete the first one and the 7th and 8th, which are for the fingers. So these are the remaining 6 angles which are going to be sent to the joint trajectory controller of the robot, and it is going to make the robot move. Okay, you will make more sense out of it when we will implement it. So this script kinematic solver should give you just an idea of the working of the library. Now it is not going to be added to the setup.py file because we are not running it through ROS. Inverse kinematic solution, the script that is mixture of kinematic solver and the controller test. It is containing the library that we just used and mixed it with the trajectory generation message that we use to publish the joints to make the robot move. Okay, I have mixed it up and make it robust through arguments. Okay, we will be just telling this script not by building again and again on Colkin, but we'll just move the end effector to this point, to this point, to this point, and it will move it. So everything seems to be working fine. Let's first run it and then we will discuss it. Okay, we need to add it into our setup.py file. Setup.py file. We need to make some additions. Inverse kinematics, and the name of the script is okay. It should be small, by the way. And this seems to be fine. So let's perform Colkin build. We have added the file to the setup file and it is ready to run, right? In the next lecture, we are going to run it because it is going to take a lot of time for testing how is it working. Inverse kinematic solution, are they useful or not? So let's move to the next video and see this inverse kinematics by IKPy. The previous lecture, we wrote the code, but we did not run it. That excitement is going to be fulfilled right now. So let's start it without any delay. We are going to be performing first the Colkin build because of the changes that I've made. I will show you the code and I will explain it. First, we need to launch the robot with the controllers. The second thing is to run the script, right? ROS2. I have written it already for you, but I don't find it, so I have to write it again. ROS2 KUKA arm, name of the script, and what in x, 2.2 in x, 1.2 in y, 1.2 in z, and O to make the claw open. If I press enter, and a lot of things have been printed, and you can see our robot has moved. Now, this is the time to test if the inverse kinematic and forward kinematic solution provided by the library is correct or not. As you might know that on x-axis, y is equal to 0. So what I am going to do is to give y-axis to be 0, just to check it, and increase the x-axis. Height is also going to be increased. I'm just making things up and giving different values to the robot so we can test if the kinematic solution is fine or not. 3.2 in x, 0 in y, and 2.2 in z. I think in z value was more than enough, so let's shift it to 1.8 and see what it does. What we have to test, if this value has made y-axis to be 0 or not. Now, the robot is looking like it is exactly on the x-axis and 0 on the y, which means the values that we gave to the robot are making the robot act like it, right? Let's build upon this hypothesis. Now I'm just going to play with the values of z-axis, 0.5 in the z-axis. And it has just moved in the z-axis. So which means to some extent our kinematic solution provided by the library is fine, right? Let me perform another test by making the x-axis negative and observe the effect. It should come to the opposite side. And yes, it has. Now, one thing interesting here is robot is not focusing on its movement. It is just focusing on one thing, and that is the end effector point should be at the point where I am desiring or I am commanding it to. So it is working fine. Let me now shift it towards y-axis. I'm going to set x-axis to be 0 and positive y-axis. Let's take a look on the output. And yes, it has moved exactly to the point where it should have been moved. So our inverse kinematic solution and forward kinematic solution by the IKPy library are perfect, literally perfect. It is a hard task to do, but these library has provided us an awesome solution. We can literally play with it. Now I'm going to close the claw and I'm going to increase the height in the z-axis and make the robot move to the negative of x, negative of y, 2.2 and negative of 1.2. It is going to be some sort of in mid. So let's take a look on the output. It should come to this point, in the middle of an x and y, because both values are provided. So you can see the claw has also been closed, and I have provided different values for x and y to see the effect. I was just confirming that the inverse kinematic solution are accurate to the robot or not. Okay, so I'm just giving them x and y values. So let's just increase and decrease the z-axis values to understand the effect. Now, if I say 0.7 and open up the claw, let's take a look on the output. It has decreased from 1.5 to 0.7 in z-axis, which is height, and claw has been opened. So things are awesome. Now let's stretch the robot. I have written some commands here to show the effect of to show a behavior by the robot. Okay, let me just paste them and observe the effect. Where is the robot? A full stretch robot in up direction. Nice. What other things I have written? Full stretch right. Let's take a look. Full stretch right. How does it look like? Full stretch right. I think a little bit more stretch can be done. Let me do it by myself. In the x-axis, make it 3.3. And yes, a little bit more stretch can be done. Yes. So we are just giving XYZ values to our robot through this awesome script that we are now going to discuss, and it is making the robot controller act in the simulation. So what this script is containing. First of all, I have followed the same pattern to obtain the UIDF file as we used to do in the launch file, the share folder thing, and we are going to utilize that concept. All of the libraries, including this major and important one, IKPy.chain, which is going to be utilized. Now, the object of this class is created the same thing as we have already discussed about the controller interfacing when we were discussing this controller test file. All of the things are same. Package, joints, timer, publisher. New things are this line or these couple of lines which are obtained from the launch files to access this UIDF file by not giving the absolute part, but obtaining the UIDF file through the share folder of our package. Then robot initialize function is called, and this function is basically taking the UIDF and making the library understand the UIDF to produce a forward kinematic solution. After that, we are providing inputs, user inputs, the values that I was giving through the terminal, these 3.5, 0.5, 0.66, these are sent into this function kinematic inverse kinematic solution. What it is doing, it is taking XYZ value and claw value, and it is giving those XYZ values to inverse kinematic solver of the IKPy and deleting unnecessary angles that we discussed earlier in the inverse kinematic solver.py file. Now the claw value are just two, O and C. I think I've just written the command for O only. If it is O, meaning open the controller. What I'm doing, I have the 6 angles for the joints. I am adding 2 more values for the fingers that I deleted earlier, and those values are going to be manually added into our robot joint angles produced by inverse kinematic solution, and they are going to be sent as a joint trajectory message so the controller can act upon it and make the robot move as desired. So goal positions are then sent into the controller. These are manually added to open and close the claw. Okay, so get FK solution is not called anywhere in the code, although it can be used to print out the forward and inverse kinematic forward kinematic solutions. And this script is very useful to make the robot move and understand how you can make your own custom robot move with the controllers that you have set. And that's all for this lecture. We will now take a look into joint trajectory controller, more features that we have, and we can utilize it to make more awesome and meaningful movement by the robot.